So I want to give you a little bit of a background on what exactly we're looking for as far as gases go, right? And primarily what we're looking for as far as gases go, we're looking for how much pressure they exert. And by pressure, we're talking about how much pressure in the surface area that we have. Now, the best example that we can come up with, and what they were able to determine back in the good old days when everybody was discovering this stuff and it was all brand new to them, is how much pressure our atmosphere is actually pushing down upon us. And what they did is they filled a little container full of mercury. Okay, the blue stuff here is mercury. And what's happening is that uh, at, at sea level, the atmosphere is pushing down on this mercury. And what they did is they took some vacuum, all right, and they put it on one end of a container. And then they released this into the atmosphere. Basically, they just put it outside, right? And then the atmosphere started pushing down on this liquid. And as the vacuum pulled on this end, the mercury was pushed up a certain amount. Okay? And it went up a certain tube. So the mercury filled this particular tube. What we're able to determine is what the distance between the level of the mercury was and the very top of the mercury inside this little column. And what they were able to determine was at these points, this amount of mercury was pushed up at sea level. So at sea level, okay, the atmospheric pressure pushes mercury up a column about 760 millimeters. Okay, and what this is a measurement of how much force is pushing that mercury. The mercury is a very dense liquid, right? And it's a metal, so it's heavy. If you've ever held a jar of mercury, you know what I'm talking about. Most people have it. But for the most part, whenever you're dealing with mercury, it's a very dense metal. That dense metal, since atmosphere is pushing down right here on the mercury, as it pushes down on the surface, it's forcing the mercury up. So long as there's a vacuum right here. Okay? And this distance is how much pressure we've got. And what we've noticed is that as we measure this, we give 760 millimeters of mercury a basic rating as 1 atmosphere of pressure. Okay, or 1 atm of pressure. Okay, that's the amount of pressure that's pushing down on this little tub of mercury. Okay, now when you look at this from a physics standpoint, what we're trying to figure out is how much pressure is going to be applied in a 1 by 1 square meter area. Okay, so how much force is being pushed down on this? And force, as we know, let me erase some. Actually, let me just use green here. Okay, force is going to be equal to mass times acceleration. And we know that the gravitational acceleration is about 9.8 meters per second here. And the force is pushing down on it. Okay? And that force is what we want to measure. Force, okay, turns out to be about 10,000 kilograms per square meter. Okay? And when we look at this 10,000 kilograms per square meter, what we're looking at and applying it is a force which has been related to what the master of physics came up. And the master of physics is Sir Isaac Newton. And we take this unit, kilogram per meter squared, and we call it a Newton. All right? So a Newton is a measurement of force. So atmospheric pressure is about 10,000 newtons, okay, at sea level. Because the atmosphere gets a little thinner as we go up, the amount of atmospheres of pressure actually goes down. All right? All right, good. And one thing that we know about this force, the amount of acceleration from all this mass pushing down, these newtons are going to be applied over a certain area. So 10,000 newtons, okay, and that's the force, right? And we're looking at the amount of area. If we're talking about area, which is 1 square meter, this is a measurement of pressure, okay? So we have force over area, and that gives the amount of push that the atmosphere is giving, or the amount of pressure that that gas is giving, just by sitting down on it. What we're going to use this as is how gas pushes on the inside of its container. So our basic measurements are going to be, we're looking at newtons as far as force goes. We don't really like using newtons, so what we do is we relate this to what's called a Pascal. And a Pascal is the amount of newtons that we have per area. Okay, so we look at this and we say, if we have 10,000 newtons, okay, and this is force, right, over 1 square meter, and that's area, okay, this is going to be our pressure, right? So this unit, force over area, we're going to take this and we're going to call this a Pascal, okay? And a Pascal, if you can figure this out, it's going to be newtons over meter squared. Okay? So that's pascals when we're talking about pascals in terms of force. And if one Pascal is going to be equal to 10,000, one atmosphere, all the pascals that we have in the atmosphere is going to be 10,000 pascals, or 1 times 10 to the second kilopascal. Okay? And that's what we talk about as far as pressure goes. Now, it's important to note when we're talking about pressure that we're talking about the amount of push that the gas is giving. Because when you think about that, it all relates to the container that the gas is going to be in. Because when we're measuring things, we can't really measure it on a planetary scale. We just don't have the capabilities of doing that. But what we can do is we can look at pressure and push on a smaller container basis. Okay, so what we're going to do now is we're going to look at the one single container, and we're going to devise the laws that comprise that container that all relate to push, as far as pressure goes, as well as the container itself, which is a three-dimensional object, so it has volume. So what are the relationships between pressure, volume, and everything else that's around it that applies as far as variables go to a gas?